Okay, so ladies and gentlemen, hello and welcome everyone. My name is Ali Thar. I'm currently the president of BOGIG student chapter, and I'll be the moderator for today's session. So today we have a new session of our program, the Monthly Talker, and we have an exceptional figure, Dr.seàn Moran. So welcome him. But before sir, you start, I have to notify about a couple of things. First of all, please do not open your mics during the session, during when Mr. Moran will be presenting, so you don't interrupt him. Also, we will have a time at the end of the session to answer all of your questions. And thank you very much for your attending. And sir, you can have the mic. Thank you very much.
Thanks, Ali. So I'm just going to take the presentation. Hopefully you can now see my presentation.
It's totally clear, sir. It's totally clear.
Yeah. Okay. So my name's Seàn Moran. As you may know, I am a chemical process engineer, and I have been since 1991. And I have been working as a freelance since 1996. And I come from a background with EPC companies. So I started off as a proposals engineer, so designing process plants, writing bids, making presentations to persuade people to buy the thing I'd designed. And the good thing about that was I got to design a lot of plants very early in my career. I was given a lot of trust, and I got to design tens of plants in the first few years of my career. I became a chartered engineer, so that's the British equivalent of professional engineer, in 1995. And since then, I've mainly worked in design, but also I've done a fair amount of commissioning, troubleshooting. And nowadays, with 33 years of experience, a lot of my time is spent criticizing what other people have done. So I work as an expert witness. I work as a troubleshooter, figuring out what went wrong with something, whether it was bad design, bad specification, bad construction, bad commissioning, bad operation, maintenance. Some combination of those things is usually the answer. Figuring out how much of each of those things is responsible for the outcome, which leads to people taking each other to court, or people making a big claim on their insurance policy. That's the kind of thing I do nowadays. I'm also an author. So I wrote 4 books so far, as well as a lot of other articles. All 4 of the books that I wrote are published through Elsevier. 3 out of the 4 were published when I was a member of the UK Institution of Chemical Engineers, and are produced under their name. I'm going to talk about a couple of these today. I'm going to talk about my first book, An Applied Guide to Process and Plant Design. No, I'm not. Sorry. I'm going to talk about my second book, Process Plant Layout. And I'm going to talk about my last book, The Dictionary of Chemical Engineering Practice, if there's time. So, process plant layout. So who's doing it? How's it done? And where is the skill in process plant layout nowadays? So I don't know if many of you have worked in chemical engineering, but usually the piping engineers, the people responsible for the layout of pipework and things of that nature, they're mostly old guys nowadays, and there aren't a lot of young guys coming through. And generally speaking, layout is no longer taught in universities, and I think this is true worldwide. So I did spend a few years as a university professor, and excuse me, I had a difficulty in teaching layout because the best textbooks were from back in the 1980s. One in particular was the UK standard text, but an awful lot of it was out of date. These books we're all from the era of hand drafting before CAD was really used. And so when I was a student, drawings were done by hand. And if you wanted a model of a plant, that would be produced. They sold little kits of plastic parts that you could use to make a scale model of an oil refinery or whatever. Now, models are produced in software, generally speaking. Very few people can do hand drafting who are much younger than me. But the textbook was good, and by chance, I had exactly the same job as the person who had written it. I was an associate professor at the University of Nottingham.
Sorry for interrupting, sir, but I think the slide is not moving. Are you moving them?
So the slide is not supposed to be moving. Does it say motivation for process plant layout?
No. It's still on the first slide, plan and layout terminology.
That is strange because I'm down as sharing.
Sir, it's a technical issue.
If you and restart.
Yeah. If you present just the window of the PowerPoint, you cannot present the whole slide. But if you share your whole screen, you can show the whole slide.
Okay.
But if you want to keep it not whole presenting and keep it with the slide inside PowerPoint, it's okay.
Okay. So, can you now see a different slide?
Yeah. Just if you present right now.
Okay.
Yeah,
so
we can see
back on the very first slide.
Yeah, we are right now.
Has it changed?
Yeah, about me, chemical process engineer.
Excellent.
Yeah, that's great. Thank you very much.
Take you up to, so there are pictures of my books. Yeah.
Yeah, they are.
There's a 3D layout.
Yeah, exactly.
Okay,
exactly.
There's the slide I was just on.
Yeah, motivation for process plan layout 2E.
Excellent. Yeah, that's the one. Excellent. Thank you, Ali. Right. So you can all hear me and you can all see my slides now.
Yeah, it's totally clear.
Great. Okay. So next slide. So what did I have to write this book? So I had this book from 1985. And at this point, I had 25 years of engineering experience. I'd spent about 5 years teaching chemical engineering. And it's useful to teach chemical engineering because I had forgotten, I guess. I'd forgotten a lot of what I'd been taught in university because a lot of it wasn't of any practical use. And also I'd forgotten what it was like not to know a lot of things that I did every day. I've been doing it for 25 years. At this point, I'd written one previous book, and I am connected to a lot of engineers on social media. Nowadays, pretty much exclusively LinkedIn. And using those social media contacts is a key aspect of how I write my books. So I write a first draft, and then I get other people to comment on it. And then I take in all their comments and I have a think about whether they're right. I guess perhaps they agree with me, perhaps they disagree, perhaps they mention something I hadn't thought about. I have a think about that. Sometimes people disagree with me, but I decide that it's my book, so I'll write it my way. But more usually, if enough people disagree with me, I reconsider my position, I do some more research, and I find that perhaps the way I was taught to do things is a way of doing things, but a lot of other engineers do things a different way, because I aim with my books to try and write it so that it's the consensus opinion. So it's not just my personal experience and my personal opinion, but it represents the consensus of opinion of hundreds of other chemical engineers. So I like to make it as true as possible. So the red words here are the key ones. I like my books to be correct, complete, and current. Especially if you're updating a book from 1985, a lot of the work that you're going to do is going to be updating things. So the first thing I had to do was take my precious book from 1985 and take a knife to it, cut the pages out, and put it through a scanner to turn it into something I could change, because I didn't have an electronic copy of the original book, so I had to make one. So there were a few key questions. There were a few things that I thought weren't right about the book, and also there were a few things that I knew that people disagreed about, and I hadn't really got to the bottom of them. So I took a few tens of practitioners and I asked them questions about things like how many stages are there of the design process? What are they called? I think I'll cover this later. Somewhere between 3 and 10 stages was the answer, but actually it's 3 or 4, but some people split them into sub-stages. What nobody ever does, now I'm not sure what you're being taught in Iraq, but a lot of what's taught as design in university chemical engineering departments nowadays has very little to do with the way professional engineers do it around the world. So once I'd done that, I produced a rough draft and produced a database of other practitioners who I found on social media who were willing to assist me. And I started an ongoing process of conversations and correspondence with those other practitioners to make sure that it was all correct, complete, and current. So, like a lot of more academic books, the original book was written by a committee, and therefore some things were covered 5 times. Some other obvious things were not covered at all. It was inconsistent. It was inconsistent in style. The different people who wrote it used different definitions of the same words, which made it quite confusing, which is something I'll come back to later. And it only offered a single methodology for plant layout. And it was a methodology that I'd never seen before. So I'd been laying out plant for some considerable time at this point, and I didn't recognize the one methodology that this book offered. It was an academic methodology. It was out of date. It had a lot of old, rather academic references. If you try to find references, academic references about plant layout, you really won't find very many. What you'll find is a lot of references for sort of mathematical exercises in which mathematicians try to make the problem of plant layout into a mathematical problem which they can solve. And they have failed. They can't do it. So the best they can do is, if the plant is all on one level and has a certain number of well-defined unit operations, it can lay a plant out to some extent. But as soon as there's a second floor, as soon as there's a third dimension, they can't handle it. And as soon as it's got anything like the degree of complexity of a real plant, they can't handle it. So those, I did read those references for completeness, but to save you time, don't bother. Actually, all of the good practical references for plant layout by people who ever laid a plant out date back to the 1980s, 1990s at the very latest. So it's practical plant layout has been completely ignored by academic research. But some things have changed. Because a lot of people in academia don't accept that things have changed, I also like to tell them how that I know that it's changed. So obviously, since 1985, engineers use computers a lot more than they used to. When I first started work as an engineer, we shared one PC between an office with 30 people. You had to book time on it. And if you wanted a program, you had to write it yourself. Now everybody's got a computer, and they've got a more powerful computer than we had back in 1990 in their pocket. So that computer was not as powerful a computer as a mobile phone. So everybody's got computers, but they're not using the computers to do anything smarter. What has happened with the use of computers is that it's made, I suppose, things like this possible. So computers have made it possible for people to communicate across the world. So you can outsource your engineering to India, where it's an awful lot cheaper than it is in the UK. And you can send drawings backwards and forwards electronically, rather than being hard copies, which are put into a tube and then posted. And then there's email and mobile phones, and so ease of communication between people and across the world. So the last job I had, quite close to where I'm working now, I was in an office, and pretty much everybody in the office was sat there with headphones on, looking at a laptop screen. Sometimes they were having meetings with people who were in the same building over Microsoft Teams. That's how used we are now to relating to each other through computers. And this has advantages and disadvantages. So things have changed, and computers are quite a bit to do with it. Computers also allow you, rather than, it used to take an awful lot of effort to investigate a potential design solution. Now you can investigate 400 and pick the best using computers. Previously, because you were doing hand calculations, you'd have to pick the 3 or 4 best ones at most and only investigate them, because investigating each one would take so much time. So it's altered design methodology to some extent. There's less intuition, there's less reliance on the skill and knowledge of senior designers to prune the number of potential solutions, which used to be absolutely necessary because of the time it took to analyze each individual one. So this also means that design outsourcing has become more normal. Companies, big engineering companies, especially those that make products, they no longer have really design departments. It all gets subbed out to design houses, sometimes in the same country, sometimes internationally. The pipers, piping engineers, have been joined by process architects. So this is a subclass of architects who lay out plant, especially in the pharmaceutical industry. And the other thing that's happened is that there are a wide range of different approaches to layout design now. So I've gone from the old edition of the book to the new edition of the book. I've gone from 1 method to 7. So there are 7 methods in the updated book. We have the process architects method, we have the pipers method, we have some more academically influenced methods, we have computer-based methods. There's a whole range of different approaches now, and they don't necessarily talk to each other. But as I said earlier, layout is, generally speaking, no longer formally taught, and also there's no real academic research into layout. So what hasn't changed? Because a key thing I used to have difficulty getting over to my academic colleagues used to be that most of chemical engineering practice has not changed. Most of what chemical engineers do all day now is exactly the same as it was in 1990 and in 1970. So the nature of the design process has not changed. Drawings are still far more important than calculations. Excuse me. And good layout is still important because, so this is from a paper, I can give you the reference if you want, but these are design errors leading to, I think, at least loss of time accidents. So these are design errors which were the cause of accidents. If you look at the bottom bar, the number 1 design error leading to accidents is bad layout. So I set out to fix the problems. which had its own problems. I'm not going to read all the words on the slide, but I've already said that the multiple methodologies in the new book, but I also included a lot of case studies. So the old book was rather dry. It's always easier to talk about engineering problems to illustrate them with a case study. And some of these case studies, it is just amazing how unwise people can be. Just how people. So I think my favorite case study from the book was so in Russia, they were making biological weapons, and Russia in the 50s, 60s, mid 20th century had these secret cities, and they had secret nuclear cities, and they had secret rocket cities, and they had secret biological weapons cities. But if you've got a secret biological weapons city, it's still not a good idea to put your biological weapon manufacturing plant right in the middle of town. And it's an especially bad idea to have the outside street separated from the dryer that makes your weapons grade botulism powder, separated from the outside world only with a single filter. This proved to be the case when the filter was taken out by the maintenance crew overnight for maintenance, and they just stuck a piece of paper on it on the machine that made weapons grade botulism, saying, "Do not start machine." Of course, somebody started the machine, and weapons grade botulism powder was sprayed out into the street. Many thousands of people died. So, bad layout, bad selection of plant site, failure to consider maintenance during design, a whole load of mistakes that happen again and again, I find. We never seem to learn definitively. We have to learn the same lessons again and again in engineering. So I asked people about the methodology, and asked them how many stages there were and how they went about it. And what you tend to find in engineering is the nature of the process drives the methodology. So even though these people sometimes were quite insistent that their way of doing things was the only way of doing things, all the ways of doing things were wrong, actually, once you took away the difference in terminology and looked at what people actually did, there was a common methodology. We can call them a lot of different things, but there's a first conceptual design stage in which we come up with the broad approach or approaches which we're going to follow in technology we're going to use, taking into consideration things like how much land we have available. So technologies quite often differ in how compact they are. So if you've got a small site, then you're quite often going to need to use more compact technologies. So in the first stage, we decide on the sort of technology we're going to use. Maybe we'll get it down to just one, but no more than one or two usually. And we tend to have a strong preference, even if there are still two left. And then we select one of those and we move to front-end engineering design, feed. Why is this? Why does everybody have staged design? Well, each of these stages of design costs more money than the last. So doing a conceptual design is relatively cheap. The feed study costs more money. Detailed design, more money still. Design for construction, more money still. Most designs don't get built. 98% of inquiries for conceptual design do not ever get built. So it makes no sense to do a fabulously detailed, highly optimized design at the conceptual design stage, although they quite often teach this in university. Nobody does that. Nobody does that because there's not a lot of money available for conceptual design. And if you spend a lot of money on conceptual design, then the design costs are 98% likely to be lost. So you'd like your conceptual design to be done cheaply. You're more committed by the time you get into feed. By the time you're at detailed design stage, usually that happens after a contract has been let to build the plant. So we know we're building it. It's just a question of counting the bolts. And then design for construction. That's taking into consideration those changes which proved necessary when we really got into the detail of the design. So everybody really always does it this way, although they may split concepts. I was recently working somewhere where conceptual design had 5 stages. I worked in other places where feed has multiple stages. The last stages, though, they tend to just be one stage. But these early stages, sometimes there are stages that happen inside a client company and then they go out to a design house. There's a number of ways of doing it, but there are basically 3 or 4. The conceptual design does the things listed on this slide. And I assume you know what PFDs and PNIDs are and unit operations. Just in case, PFD is a process flow diagram. It's a graphical representation of the mass balance, essentially. A PNID is a piping and instrumentation diagram. And this shows the instrumentation. It shows it's a topologically accurate representation of the plant, not to scale, simplified, but it shows quite a few key aspects. And it's the signature drawing, generally speaking, of the chemical engineer. And it's also the way in which we communicate with the people who do process control. They tend also to be able to read PNIDs. Generally speaking, the other disciplines cannot read PNIDs. So during the conceptual design, you're going to specify the unit operations that you're going to use, and you're going to lay it out. Because if you haven't laid the plant out, then you don't know how long the pipes are or how big they are, and therefore you can't have sized your pumps. So even at conceptual design stage, in the real world, we lay the plant out. Also, if you don't lay the plant out, you don't know if it's going to fit on your site. And the plant does have to fit in the space available. Or if you don't already know where it's going to go, you have to take into consideration when you're pricing it, how much land it's going to take up and the cost of that land. Yeah, the other thing that tends to be produced during the conceptual design stage that I've not included in this list is a pricing. Because without a pricing, well, all designs are more or less equal, or you can make the mistake that I've seen made, where people split what they call the technical and the commercial evaluation in 2. And they say, just tell us what the best technical solution is. There is no best technical solution. All design has to balance cost, safety, and robustness. By robustness, I mean how well the plant can cope with a range of operating conditions. So generally speaking, in university, for simplicity's sake, people are taught to assume steady state. In the real world, there is no steady state. You have to be able to handle a range of values of all of the key process operating parameters. And also, you have to be able to not have the plant explode if you go outside of those acceptable ranges. It has to fail into a safe condition. So cost, safety, robustness, or you've not really designed anything. So usually at the end of this process, the end of all of these processes, there's at least one review where more senior engineers and management review what you're thinking of doing, and then this is proposed. It's either proposed internally, or very often it's proposed by a consultant or a contracting company to a client. And the client then decides whether or not they want to do this. And 98% of the time, they don't. They don't want to do it. They decide to do something else. It costs too much. It doesn't fit on their site. They decide to do it later. It doesn't get built. So when we move to the next stage of design, we're looking a bit harder. We produce the same basic deliverables, PFD, P&ID, etc., a better layout drawing. Now we have a multidisciplinary review. We don't just have a management review. Now we're going to get the electrical engineers and the software engineers and the mechanical engineers, all the different disciplines involved. We're going to get the environmental engineers involved. We're going to the architects. And quite often, after you've done that, you're going to need to redesign it. So again, one of the deficiencies of like all university engineering courses is a design project done at university almost always involves a single discipline. So you've got a design done by chemical engineers, and the mechanical engineering, electrical engineering, software, etc. aspects of it are very poor, obviously, because you've not got anybody who even knows student level what those different disciplines need. So, but even in the real world, with experienced engineers who know from experience what the electrical engineer is likely to need, and so on, you'll have a multidisciplinary review, and there'll be a redesign to take into consideration those comments. And there may be multiple stages. There may also be at that stage a HAZOP, although HAZOPs are usually better the later in the design process they're done. But if it's reasonably fixed in the feed stage, you can have a HAZOP. HAZOP should not involve redesign, because HAZOP is not, strictly speaking, a design review. It's intended to catch aspects of the design which are unset. There shouldn't be many pages of outputs from a HAZOP. That is not a good sign when it comes to the degree of effort that went into the design, if that's the outcome. There shouldn't be a lot of things coming out of a HAZOP. I'm assuming you know what a HAZOP is. If not, ask me questions about it at the end. So anyway, it's redesigned, it's reviewed again, and if everybody's happy, it's proposed to go to the next stage. And the next stage tends to be a contract to build the plant. So the reason why identify team is the second item on this list is because usually there's a proposals team and there's a construction team. And when we go from feed to detailed design, we hand over. In a good company, there's a good handover. In a good company, the construction team make sure they understand what it is that's been proposed, and they maintain open lines of communication with the people who proposed it. And a team is identified of people who are going to be able to work up that outline design into something that can be built. So now we have lots of different disciplines, not just reviewing the design, but also doing detailed design in their different disciplines, talking to each other to make sure that all of the different disciplines are working together. And also now we're doing a detailed layout. So information is coming into the piper or whoever's doing the layout from chemical engineering, from electrical engineering, from mechanical engineering. Sometimes the person doing the layout will be a mechanical engineer themselves, in which case they may well do, or at least lead the mechanical design. There's lots of different ways of doing it. Note the word conservative in front of redesign. So what's not good is if the people responsible for construction assume that the people responsible for proposals are idiots. And therefore, they just assume that if there's something about the design they haven't seen before or they don't like, that what they should do is redesign it from scratch. Because the thing is, it may well be that the thing that they would like cost a lot more money. And the reason why it didn't go in at the earlier stage is because if that more expensive way of doing things went in at the earlier stage, the company wouldn't have won the job. And if they do it the more expensive way, they're going to guarantee that they lose money. At the detailed design stage, we're definitely going to do a hazard and operability study. Once all of this is done, and it's all signed off by all the discipline heads, proposal goes forwards to the client. Here's our detailed design. Please approve it within 14 days, and we will get started with construction. Now, in the real world, generally speaking, the third line here, simultaneous procurement, construction, and design. As we go through each of these stages, more time is lost. Usually, by the time we've reached design for construction, we're already late. So what usually happens is you start on site without the design complete, and the construction team are both simultaneously helping with the design and starting on the construction. So now we're doing a very, very detailed design and a very, very detailed layout. And this is happening in an environment where elements of the design are changing. We try to change it as little as possible, because the later on you are in this process, the more it costs to change your design. So the most expensive kind of changes to make to your design are changes at the point where you're on site. It is a great deal cheaper to move a virtual line on a CAD drawing than it is to move the thing that that line represents in the real world when it's made of steel or concrete or whatever. So there are reviews, and we are certainly procuring it, buying in the equipment at the same time as we're building it, at the same time as we're designing it. And sometimes, yeah, we're even commissioning it whilst we're still waiting on some pieces of equipment. We're commissioning parts of it, but commissioning is not something I'm going to cover during this talk. So process layout is iterative, like all engineering design. So you come back to it. Increasing degrees of sophistication, back and back and back again. In the original book, the 1985 book that I updated, he said you lay out the site, then you lay out an individual plot, and then you go back and lay out the site again, and you go round and round that way. It doesn't really matter which way you do it, as long as you get through all of the different levels of design. Now, I'm trying to remember if I've got, let me just check. Right. So for those of you who are familiar with process plants, they tend to be laid out quite often in a sort of grid structure, and the squares inside the grid approximately are called plots. You can lay out, so you have equipment level design, then you have plot level design where you're laying out one of these blocks, and then you have whole site level design where you're thinking about the whole site. So reality may well be messier. So I give 7 different ways of doing it in the book. None of these ways of doing it are followed perfectly. Quite often, different people are using different methodologies, and then somebody's integrating all of these different methodologies. The best thing about the original book is repeated hazard assessments. So hazard, HAZOP, things of this nature, which were very novel back in 1985. And they are definitely something which should be integrated in good process layout design. So people don't teach layout. Why should they teach layout? So if you believe in multiple intelligences theory, it's a little questionable, but whatever it is, laying things out and seeing a 3D model of things in your head it's a thing that a lot of engineers are very good at. And if you teach layout, you're giving the natural engineers a chance to shine, a chance to show that they can do something other than calculus, that they can actually lay things out in space, arrange things in space in a clever way without mathematics. It also gives you an additional dimension to evaluate student designs. And lastly, and perhaps most importantly, so I used to get a lot of student work when I was a lecturer, and they would say, using HYSYS, underneath a pump, it would give a kilowatt rating for the pump. And I say, how have you got a kilowatt rating for your pump? Well, HYSYS told me that. Well, HYSYS couldn't know that, because if you don't know the dimensions of your pipe, if you don't know its internal diameter, and you don't know how long it is, you don't know how many bends it has in it, then you cannot do hydraulic calculations. That means you cannot know what head a pump has to deliver. Therefore, you cannot know what its power requirements are going to be. So, one of the reasons I used to like to teach students layout was for enhanced employability. Students who have been taught to lay plant out have a skill that very few university graduates have nowadays. And employability at the place where I taught this, the university went from 22 of 25 UK chemical engineering departments to 3 on employability as a result of having a higher practical level of knowledge in the green graduates. So we can ask can take questions there on the layout part of the talk.
Yeah, sir. Yeah, you can have any question. Ladies and gentlemen, you can open your mics if you want and ask Mr. Seàn any questions you like. So just feel free. Anyone has any questions? You can write it down in the comment section or the chat box, and I can deliver it to Mr. Seàn. So, sir, I have a question myself while waiting for the audience to. Was it what you said? HAZOP. What is it?
Oh, okay.
Yeah.
So a HAZOP is a hazard and operability study. It's have you heard of that?
No, actually, no? This is my first time.
Okay. So on one level, it's better that you've never heard of it than that you've heard of something else with the same name, which isn't it. Okay. So quite often in UK academia, they teach something called HAZOP, which isn't it. So what HAZOP is, it's a structured way of thinking about all of the different things that could go wrong on a completed design. So you take things like flow, pressure, temperature, etc. So you have flow, pressure, temperature, etc. And you have more of, less than, different from, and you permutate those pairs of words, and you go through your design one liner on the P&ID at a time. So let's take the first line coming into our oil refinery, and we say, what would happen if it was hotter than expected? What would happen if it was colder than expected? What would happen if the composition was different from what we were expecting? And then you have a committee of people, maybe 10 people, all different disciplines, and they will think about that. They'll come up with various different things that might happen. And if any of those things is significant, then somebody needs to make sure that that adverse event is considered. Is that clear? I mean, I've never tried explaining it just in words.
No,
before.
it's so clear, sir. Thank you very much.
Okay.
And there is multiple questions in the chat box. I will read them for you. Okay, sir?
Okay.
So our friend Shahram says, as a fresh graduate, do we have to know all of the aspects of plan layout? I have graduated this year. We had plan layout, but only the definitions and some basics, but not the actual theory and purpose of plan layouting.
Okay. So you certainly don't need to know all of it. So I think my book has 750 pages. And that isn't all of it. So you definitely don't need to know all of it. But you could know more of it. I guess so. I have written some shorter articles in the Kirchhoffmer Encyclopedia and some other places. I wrote a short article for Chemical Engineering magazine. I think a few short articles for Chemical Engineering magazine that have some outlines. So you could try reading the Chemical Engineering magazine articles I wrote, or you could get a copy of the book. But it's a big book. I do cover shorter explanations of the layout methodology in my first book, An Applied Guide to Process and Plant Design. So that has one chapter on layout, and that might be a place to start. And that's a book that's specifically written for new graduates, for first 5-10 years of their career, just to understand the difference between what they were taught in university and what chemical engineers actually do.
Okay, sir. Okay. Next question, Doughton says, given the importance of layout, why does academia neglect its importance?
Okay. Well, now I don't know how it is in Iraq, but in the UK, academia is all about academic research. Academic research tends to be published in scientific journals, and scientific journals are interested in science, and layout is not really science. It's more of an art, and the people who are really good at it. So a lot of the people who I interviewed to get the real detail of how layout is done, quite a few of them didn't have degrees. Quite a few of them were older than me, and they're from a time where the people who laid out plans were taught to do it. They left school and they went to work drawing on a board, and then they were taught as a craft, starting with production of isometric drawings, becoming more and more complicated. It was a craft, and a lot of the knowledge was never written down anywhere. And this was part of the exercise that I did. I sort of getting these old guys to tell me the secrets and the rules of thumb and all of their little tricks and hard-won knowledge. So most academics nowadays in engineering departments, I don't know how it's in Iraq, but in the UK and a lot of other countries, have never actually designed anything. And the thing about layout is, more so than any other part of process plant design, it's not mathematical. It's visual, it's graphical, it's to do with drawings. Again, most academics in engineering departments, in chemical engineering departments, can't draw. They can't use. So I ended up, when I was an academic, I ended up teaching all of the students to use AutoCAD, because I was the only person in the department who could use AutoCAD. So I cover it in my books, but essentially, chemical engineering especially has become very, very mathematical. There's not a lot of emphasis on drawings. There's not a lot of practical knowledge of how practicing chemical engineers go about design. So I've written some quite long articles on it, but that's a summary of the key reasons.
Okay, sir. Thank you very much. And I think you answered this question, but I will read the comment again. I want to gain knowledge in a plan layout because I love it and I have abilities to do. What is the best way to start?
So if you want to do it practically, I guess try and get a job working for a company that really lays plant out. Obviously, I'd like to say well, you can read my articles and buy my books, but that is second best. What is best of all is to do it. So get a job working for a design house or a company that's really doing the detailed design of plants. You don't have to lay out whole plants, because laying out a plot or laying out equipment, or even doing ISOs, which is where the old school pipers used to start. It's all part of learning the process, and it's an opportunity to talk to more experienced engineers. All of the useful stuff that I've learned about engineering, despite I've got a PhD, all of the useful stuff that I learned from older guys. I learned from people who've been doing the job for decades, and they taught me how not to do it, which is as important as anything else. And then they taught me how to do it. And a lot of people think that engineering has changed radically. It really hasn't. The way plant is laid out is it's different, because we do have 3D CAD programs, and we've got laser scanning and so on. But these are just tools. The basic intuitive skill of laying plant out is exactly the same as it always was.
Okay, sir. Thank you, sir. And just you said you talked a lot about your books, sir. So how can we get it? Can we get it online as a digital version?
So you certainly can. You can certainly buy them from Elsevier or from Amazon or whoever. They are, I'm afraid, very expensive. I've tried asking Elsevier to make them cheaper, and they absolutely will not, which is unfortunate. So I am not going to suggest obtaining illegal copies of them, but if you did want to do that, you wouldn't find that very difficult, judging by the number of links I see to illegal copies of my books, even on LinkedIn. So obviously, I'd like you to buy them, but if you can't afford $200 for each book, then yeah, you may find. I mean, if you're in a university, the university library can get them for you. So obviously, although I don't actually make any money out of that, obviously I'd prefer you didn't encourage people to illegally share my work without payment. But so yes, ideally get them legally. Those of you who are in universities, the university library should be able to get you copies of them legally.
Okay, sir. Thank you very much. And lastly, sir, asking for myself and for all the audience, as a fresh graduate or as a still student in chemical engineering profession who are going to work in this profession, what is your best advice you can give us?
That's a broad question. I guess I could you be a little clearer? I mean, I assume you want to work as chemical engineers.
Yeah, exactly.
Yeah. So how's employment in Iraq? Is there plenty of work for young chemical engineers?
Actually, we have an oil and gas field, so we have opportunities, but it's not that big of an opportunity to all of us to work. So we need real qualifications.
Okay. I guess the thing I'd say then is, especially in a country which very much looks to oil and gas, there's chemical engineering other than oil and gas, I guess is what I'd say. So I've worked in oil and gas, which is why I've been in the Gulf, but I've also done a lot of stuff to do with water and effluent treatment. I've done stuff to do with food. I've done stuff to do with pharma. So unless you're a petrochemical engineer specifically, in which case it's a little tricky, chemical engineering can be used for any process industry. So I've worked in mining, pharmaceuticals, municipal and industrial, water and effluent treatment, food, energy. So there's a wide range of potential fields where you can apply chemical engineering skills, and especially if you're in a country where that's very much focused on oil and gas, these can be good opportunities. Other people aren't thinking of them. And I guess the other thing that I'd recommend for those of you who really want to be designers, a lot of people want to get a job as a process engineer. My first jobs were not as process engineer. My first jobs were as proposals engineers. Proposals engineers get to do more design of plants that get built than most process engineers see in an entire career. You have to design lots of plants simultaneously. You've got to focus on all the important things. You've got to focus on cost and safety and robustness. And you've got to do it under time pressure. I'm 62 now, so I wouldn't enjoy that job. But when I first came out of university, I loved it. Yeah, always having the pressure, always having new things to do. It was exciting, and I got to travel around the world. And so, yeah. So think about proposals engineering rather than process engineering. Think about industries other than oil and gas.
Okay, sir, that's great. Thank you very much. And we have our friend Seven Akram. He wants to ask you. So, my friend, have the mic. Can you hear us?
Hello, Dr.seàn, dear professor.
Hello there. Good
Thank you
afternoon.
so much for sharing your information. According to your previous experience, I would like to ask you a question, especially for chemical engineers.
Okay.
You prefer to go to operation first or go to process?
So, I guess it sounds like you're describing two parts of an operating company. So those are conventional terms for two parts of an operating company. So I guess my question is, personally, neither. I am not a person who enjoys the operational environment. I like to work for contracting companies, and a lot of my experience has been in contracting companies. So I quite often work nowadays for operations companies. So I guess but looking at those two parts of an operating company, certainly the process engineer role tends to be more mathematical and technical and more like the things you learned in university. So if you liked the things you did in university, it could well be that process engineering is more your kind of thing. Whereas the operations side of things, actually a lot of that is to do with people rather than things. Well, that's certainly been my experience by observation. So I guess it's, are you a people person, or are you a person who enjoys technical things more than interpersonal interactions, or the other way around?
He's asking you, Seven. Yeah.
Sorry, I didn't get it very well.
He's saying, are you more like interactive with people or with technical stuff?
Actually, with people, with the teams.
Okay, so that's more operations.
All right, thank you so much for this information. And also another question for, our Iraqi oil fields. We have a lot of oil fields, gas fields like this. You prefer to go at the beginning for the fresh graduates, I mean. You prefer to go with the oil and gas or chemicals For example, H2SO for sulfonic acid, things like this. You prefer to go with oil and gas or chemicals?
So,
Which one has
personally, neither. That I work in those areas, but both of those companies tend to be really large companies, and I tend to prefer working for EPC companies because they tend to be smaller, tighter teams, and more focused on short-term projects rather than working at the same place with the same people for many years. So I guess this isn't a question that has a right answer. Again, it's a question of what do you enjoy. So both chemical facilities and oil and gas, providing we're talking about oil and gas refining rather than sort of primary production, which is quite different, they're essentially very similar. It's a facility. You're processing chemicals, where you're taking in something raw, you're changing things, you're producing a refined product. I don't see a lot of difference between them. There is a difference in culture to some extent, but it's not that big. There's a lot of crossover. So people call, I guess, oil and gas processing and let's say chemicals, especially bulk chemicals, this is what they call the traditional chemical process industries, and they're a continuum. I guess in between the two, you've got petrochemicals, which bridges between chemicals and petro. But what they all have in common is that you're working in a production facility, and there's a third option, and the third option is not working in a production facility, working in an EPC environment, designing, constructing, commissioning, and then when it's done, leaving and going on to the next project. Now, I'm the sort of person who enjoys a project that has a defined start and finish. And again, it's back to the question of whether you're that sort of person or whether you're the person who wants. So I live near Derby, and in Derby, we make Rolls-Royce jet engines. And a lot of the people I went to school with spent their entire working lives making Rolls-Royce jet engines. And I would have hated that. That is not me at all. I like to go somewhere, define a problem, come up with a solution, explain the solution, and leave. So a lot of these questions are to do with, it's back to you. It's what sort of person you are, and maybe you don't know yet. Maybe what you have to do is try some different things and find out which of them you enjoy, or maybe you already know.
All right, thanks so much for sharing your information.
You're welcome.
Okay, Mr. Seàn, I have a question myself.
Okay.
Taking like anybody who wants to work in the field of chemical engineering in general, all the professions that you mentioned, do you consider or do you advise these fresh graduates, green graduates, to take master or PhD, then go working? Does it have any benefits for us to take them in the working environment?
I don't think so, generally speaking. Certainly, so I did a master's degree before I went to work as an engineer, because in the UK, a master's degree is required to, that's the sort of entry-level qualification in chemical engineering. It's an MEng. When I graduated, that wasn't the case. When I graduated, a bachelor's degree was the engineer's degree, and having a master's degree did give me a slight advantage, although it matters where you got your master's degree from. So, and a PhD, so I did do a PhD, very late in my career, and I have a deeper understanding of engineering than I did before I did it. But at the same time, I don't know that that's made me a better engineer. It's made me better at criticizing other engineers, but I don't know if it's made me a better engineer, because I think sometimes you can understand things too well in engineering. Because a lot of what engineers do every day doesn't have a lot of scientific foundation. And doing a PhD made me realize this. But too many people do PhDs. There are a limited number of places, limited number of jobs for people with PhDs. They tend to be in sort of research-centric industries or research-centric parts of industries. So in the oil and gas industry, there are a small number of really, really well-paid jobs for people with PhDs. Unfortunately, there are an enormous number of people with PhDs who did a PhD because they didn't know what else to do. The people who it tends to be worthwhile doing a PhD are the people who have a passion for the subject. They're not doing a PhD because they can't think of anything better to do. They're doing a PhD because they're so interested in some small aspect, because that's the thing about a PhD. You'll become an expert. You'll know absolutely everything about absolutely nothing. You will know an enormous amount about something that no one else will be interested in. Because in order to have that depth of knowledge, the breadth has to go down very, very sharply. Now, if that thing that you know everything there is to know about is worthwhile, then doing a PhD is an excellent investment. But if it's not, it'd have been a lot better to go to work and spend those 4 years learning how to be an engineer.
Okay, sir, this is like pretty good and maximum like valuable advice. Thank you very much, sir. And we appreciate all the information that you gave us. We really appreciate you being here with us, giving us all these sort of information as fresh graduates, as PhD or master holders, and as students ourselves. Thank you very much, sir. We appreciate your consideration from the beginning, your contact with us, and we really appreciate your appearance here. Like, thank you very much.
Thank you, Ali. You're very gracious. So thank you all for turning out, and enjoy the rest of your day.
Thank you very much, sir. So this is the end of this session. Thank you very much for your attendance, people. Thank you very much, sir, for your showing, and you can have a good day. Thank you very much, sir. We appreciate it. Thank you.
Bye-bye.
Goodbye, sir. شكرا جزيلا للحضور جميعا. نتمنى نشوفكم بسيشنات جاية إن شاء الله، ونكون على تواصل أكثر وبكورسات جديدة أكثر. أتمنى استفادتوا من كل المعلومات. شكرا جزيلا، ونشوفكم محاضرات جاية. مع السلامة.